Hello everyone. Today's math challenge is about return flight journeys question. There is a common knowledge about the speed of an aeroplane in the air, which is heavily influenced by the speed of the wind. If you travel a lot between New York and London, you will notice the flight time from New York to London is always shorter than the flight time from London to New York. This is because in the North Hemisphere, above the Earth, there is a constant wind blow from the west to east. So if you fly from New York to London, it is a bit like you are running alongside the wind, and if you travel in the opposite direction, it is more like you are running against the wind. Of course, in the reality, the situation is very complicated, and here we just set some simple rules. For instance, the speed of plane itself is v, so this is the speed traveled by the plane in the still air, and the speed of wind is w. Of course, the speed of the plane v is much higher than the speed of the wind w. And if the plane flies in the same direction of the wind, we will define its actual speed to be v plus w, and if the plane flies against the wind, we will define its actual speed to be v minus w. Hopefully it makes some sense to you. Now a plane is making a return journey between two airports A and B. There are two scenarios. In the first scenario, there is no wind at all, and in the second scenario, there is a constant wind blow from A to B. So here is the question. In which scenario the plane will take a longer flying time for this return trip? Or do you think it will take the same time? As you can see, there is no number involved in this calculation, so this math challenge is a good opportunity to train your skills in algebra, which you need to deal with the letters and symbols. And you can pause the video here and spend as much time as you need, and then we come back for the answer. Okay, let's have a look at the answer together. So firstly, let's set the distance between the two airports A and B as small d. So the time for the return journey in the first scenario can be easily calculated, and this total time t1 is equal to the total distance 2d divided by the constant speed of airplane v. But in the second scenario, it is far more complicated, and we have to split the whole journey into two halves, the outbound flight and return flight. So for the outbound flight, the total distance is d, and because the plane flies alongside the wind, the speed is v plus w. So the total time for the outbound flight is d divided by v plus w. And for the return journey, because the plane flies against the wind, its speed is equal to v minus w, and the total time is d divided by v minus w. So the total time of this return trip is equal to d divided by v plus w plus d divided by v minus w. To compare T2 and T1, we have to do some mathematical processing on this expression. So the first thing we can think of is to combine these two fractions. However, they have different denominators. You cannot directly add them together. So the easiest way we can find the product of these two items as the common denominator. So this indicates us for the first fraction, we can just multiply v minus w in the brackets on both top and bottom. And for the second fraction, we can multiply v plus w in the brackets at both top and bottom. So it's something like this. Okay, and from here, for the top, it is very easy to open these brackets by using d to multiply v and w and keep this symbol minus or plus the same. And for the bottom, if you calculate v plus w times v minus w in the brackets, actually we can use a very important formula in the mathematics. So when a plus b times a minus b in the brackets is equal to a squared minus b squared. This relationship is very important, particularly for its reverse use when you want to factorize this mathematical expression. Anyway, for the bottom of this fraction is equal to v squared minus w squared, and for the top, you can open the brackets. So T2 is equal to dv minus dw divided by v squared minus w squared plus dv plus dw divided by v squared minus w squared. Because these two fractions, they have the same denominator, so we can add them by keeping the same denominator and adding the numerators. So T2 is equal to dv minus dw plus dv plus dw divided by v squared minus w squared. So the good thing here is this minus dw and this plus dw, they can cancel themselves out, leaving 2dv divided by v squared minus w squared. So T1 is equal to 2d divided by v. To compare T2 and T1, at least we can make the numerator the same. So here we can use v to divide both top and bottom of this fraction. So the top 2dv divided by v is equal to 2d, and the bottom v squared minus w squared divided by v is equal to v minus w squared over v. So here we can compare the T2 and T1 properly. Firstly, you have to agree with me. Since the speed of wind w and the speed of aeroplane v, they are all positive values, no matter what values they have taken. So this expression w squared divided by v must be a positive value, and v minus a positive value, so this result must be smaller than v itself. And here for the T2 is 2d divided by v minus w squared over v. So this divided by a value smaller than v. So the value of this fraction must be greater than 2d divided by v. Okay, because they have the same numerator, and whichever have a smaller denominator must have a greater value. So that means T2 is greater than T1. So that means in the second scenario, the time spent by the aeroplane will be longer. So if we look back in the second scenario, for the outbound journey, you have taken some advantage of the speed of wind, and for the return journey, there is disadvantage. So that means the advantage and the disadvantage, they cannot cancel themselves out. So that means unless the wind will change direction halfway, otherwise it is better to travel in the still air. Okay, thank you very much.